All right, well, we've talked about rivers. Now we're going to talk about glaciers. And you might think of a glacier as a river of ice, and sort of, not really. We'll talk about how they work, and let's just get started. So, a glacier is a flowing mass of ice. And one of the key concepts to keep in your mind, and I'm going to repeat this more than once, is that the primary way glaciers move is by flowing. You might think, hey, it's ice, it's slippery, and there is some slipping, but the primary motion is through what we call ductile flow. The ice, which is a solid, actually is capable of flow. So, how do you make a glacier? Well, that's actually pretty easy. Pile of snow. So, we're not actually freezing a bunch of water, so it's not a frozen river. The way that you make a glacier is that you accumulate a large quantity of snow. And snowfall has a lot of air in between it. So, what happens over time is more snow accumulates on top of the old snow, and that compacts the old snow on the bottom. If you make this pile thick enough, the snow at the bottom turns into little ice crystals and then ultimately into bigger ice crystals. And really, it's kind of a metamorphic rock. It's a rock that is formed through high pressure and temperature, causing the ice crystals to recrystallize and get bigger and lock together. There still is going to be some trapped air. It mentions here that it becomes kind of bluish. But that's really how our ice forms, is that we have to accumulate a lot of snow. And in class, one of the things I like to do is just ask the students, how much snow do you think, actually, how thick do you think the ice has to be before the ice at the bottom starts to flow? Because that's our next slide. Most of the flow that we have in a glacier is ductile flow. And you'll notice on this little drawing from the book, it says irregular dry interface can lock the base of the glacier to the ground. So basically, and this especially occurs in winter, the bottom of the ice actually freezes to the ground, and yet the ice still continues to flow forward. So to get this ductile flow, it turns out we need to have at least 150 feet of ice. That's how much ice it takes in order for there to be enough pressure for the ice at the bottom to actually flow. If you have less than 150 feet of ice, it's not going to flow. If you can get some water down there at the base of the glacier, then the glacier can slide. And so we do have some slippage as well, and very often the slippage occurs in the summer as the top of the glacier experiences some melting. Some of that water finds its way to the bottom and acts as the lubricant at the base of the glacier. But the thing to remember is ductile flow, number one, and the slipping at the base is the less important of the two. So, we make a glacier. We build up a bunch of ice, and that occurs in what we call the zone of accumulation, which is going to be up here. If you look at a picture of a glacier, an aerial photo, for example, the zone of accumulation is typically going to be white year-round. And this is the area which keeps at least a little bit of snow from the prior year. So in the summer, it's not accumulating any more snow. Things are melting, but there's enough snow at the top in the zone of accumulation that by the end of the summer, the end of the melting season, there is still at least a little bit of snow from the prior year there, and then we're adding the new snow on top of that old snow. That's what it takes to accumulate a glacier. Now, the end of the glacier down here is where it's melting, and the zone of ablation is the area where by the end of the summer there is no fresh snow left on top of it. The line between those two is called the snow line. For a glacier to advance, your glacial budget has to have more accumulation than melting. If the melting exceeds the amount that's being added, then the front will slowly melt back. And one of the things to remember about a glacier is the ice is always moving forward. The ice does not flow backwards. Remember, we're adding pressure here, and that's pushing the ice out through that ductile flow. If we don't add enough snow here, the ice doesn't move backwards. We just don't add enough new ice to replace what's being melted at the front, and then the front starts to retreat or melt back. So that's how the budgeting works. So how do glaciers do their work? What kind of work do they do? It turns out that glaciers can erode. Glacial ice, if you look at the hardness of ice as a mineral, because glacial ice counts as a mineral, the hardness of glacial ice is actually pretty low. It's in the 2 to 3 range, which means that it's not going to be very effective at scratching at rocks, which are made up of minerals that are mostly much harder than ice. So what happens? Well, remember we said during the summer you get a little meltwater at the bottom of the glacier and it can slide? Well, when that happens, the other thing that meltwater can do is it can actually pick up rocks, and that's what we call plucking. If you change the conditions of the ice in such a way that there's some water available at the base of the glacier, when that water refreezes, it can refreeze around sediments and pick them up. They then become part of the glacier. And so that's what you can see right here, plucking rocks. Once they're plucked, they are now frozen into the ice, and now they've turned the ice essentially into a piece of sandpaper. If you want to buff something down with a piece of paper, you can try, but you're probably going to wear out the piece of paper. But if you glue some sand to that paper, you have sandpaper, very effective abrasion, or for abrasion. Same thing happens with glacial ice. The ice itself has a pretty low hardness, but if you freeze a bunch of rocks into the bottom, those rocks can then do the work. And so on the right-hand side, you can see scratches left in bedrock, which we call striations, and glacial grooves that form because of all this material being frozen into the bottom of the ice. That material is then carried down the glacier. Now remember, with rivers, we said rivers can carry material through suspension, bed load, and dissolved load. Glaciers aren't really following those rules. In a river, the material gets picked up and dropped off based on the energy of the stream. Things like the slope of the stream, the gradient, how fast the water's going, how deep the water is, all of those affect how big the material is that's going to be picked up. Those rules don't apply to glaciers. Once something is picked up in the ice, it's going to stay frozen in the ice until that ice melts. Size does not matter to a glacier. It will pick up large things, little things, everything in between, and move it all together down to the end of the glacier. So the glacier is acting more like a conveyor belt. It doesn't really respect the size or the weight of the material it picks up. And we'll see in the deposits that we find that are left behind by glacial ice, we get this wild mix of sizes, everything you can imagine, from boulders bigger than a house to little tiny pieces of sand and clay. It all gets moved together and dumped together. A river and the other things that we'll talk about later in the semester, none of those would do that. So it's kind of a unique feature of glaciers. So what do these deposits look like? Well, here's a mountain glacier. You can see the piles of material that were left at the front. This thing has been melting back. but it leaves piles of material on the sides, at the front, and underneath the ice as well. These deposits that are left by the ice are called moraines. The moraine at the front of the ice is called the end moraine. The moraine along the sides of the ice, those moraines are called lateral moraines. And the moraine that's under the ice is called ground moraine. And a fourth type of moraine we find in the middle of the ice. You can see that pile of material in the middle of this mountain glacier here. That material is called a medial moraine because it's in the middle of the ice. How does it get there? Well, if you have two tributary glaciers coming together, the flow of the ice just goes down the valley. And so the lateral moraines that were on the sides that came together, they end up being carried into the middle and making one of these medial moraines. So lots of different moraines: end moraine at the front, ground moraine underneath, and lateral moraines on the sides, and then that medial one in the middle. If we look at this picture of the Midwest, which we'll look at a little more closely later, glaciers came down through Lake Michigan and pushed into northern Illinois, and you can actually see a little pile of material right there. That's an end moraine, and then the flat area behind it is ground moraine. Here's another end moraine that goes about as far as Mendota, Princeton, and Bloomington and Peoria, and there's ground moraine behind that as well. So we see these same moraine features, but on a much larger scale. This picture is from your book, and it also shows you, I kind of like looking at a real glacier better, that in front of the glacier, what does the meltwater do? Well, the meltwater carries sediment with it, but the meltwater behaves as running water behaves. And so the meltwater leaves layers of material that are nicely sorted, and they're in layers. And so we call this stratified drift or outwash, because it's washing out of the front of the glacier. And so the outwash, which you see here, has all the characteristics of sediment that was moved by water. So it's in layers, it's nicely sorted. Let's take a look at the difference between those two. And this is one that when we have face-to-face class, I ask students a question of. So maybe this week when we have our Zoom session, I'll do that as well, see if anybody watched this video. But you can test yourself. Which one of these was deposited by the ice, so would be counted as kind of moraine, and which one of these was deposited by water? Which one's in the outwash? And there's a little bit of a trick to it, but not much. So if you said that this one on the right was deposited by the glacier or by the ice, you're correct. This is ice contact deposit. You can see that it doesn't have any layers in it. It is not sorted. It's got big things and little things and all kinds of tiny, tiny stuff in between. So this is classic ice deposit material, all different sizes and shapes just dumped together. This picture on the left is our outwash deposit. It's actually from a lake that was in front of the glacier. And so we get very fine layers of silt and clay that have settled out of that lake water down into the bottom. Because everything freezes up in the winter, the sediment deposited in the winter is not quite the same as the summer. And so we get these bands that look like tree rings. Now you might wonder, well, what the heck is going on with this big rock sitting in the middle? This is what we call a drop stone. If we go back to this picture here, you can imagine if the area behind this end moraine were filled with water, that's what we call a proglacial lake, and an iceberg floated out there. As that iceberg melted, any large stones in that ice would be dropped out onto the bottom. And so that's what happened with this stone. So that's how we know that this was a lake in front of